Vibrational spectroscopy. Infrared spectroscopy is one of the most important and widely used analytical techniques available to scientists. It is based on the vibrational motions of atoms in a molecule. The infrared spectrum is commonly obtained by passing the infrared electromagnetic radiation through a sample that possesses a permanent or induced dipole moment and determining what fraction of the incident radiation is absorbed by a particular energy. The energy of each peak in an absorption spectrum or a transmittance spectrum corresponds to the frequency of vibration of a molecule part, therefore allowing qualitative identifications of certain bonds that are present in a molecule. An IR spectrometer usually records the energy of the electromagnetic radiation that is transmitted through a sample as a function of wave number or frequency. Therefore, the spectrum will show the x-axis either in the units of wave number or frequency. So nowadays, the total spectrum is analyzed by interference process and converted into the frequency or wave number range by means of a mathematical process is known as the Fourier transform. The Fourier transform infrared, or in short form FTIR spectroscopy, has dramatically improved the quality of IR spectra and minimize the time required to obtain the data. So now we will look into how does this infrared radiations produce the spectrum when it is directed to the sample. Before we look into the quantum mechanical harmonic oscillators, we will introduce the classical harmonic oscillator to build an intuition that we will extend to the quantum world. A classical description of the vibration of a molecule is needed because the quantum mechanical description begins with replacing the classical energy with the Hamiltonian operator in the Schrödinger equation. It also is interesting to compare and contrast the classical description with the quantum mechanical picture. So the concept begins with the simple harmonic oscillators model. If we consider the bond to behave like a mass on a spring, then this restoring force F is proportional to the displacement, which is written as R minus R equilibrium. The distance here referring to the displacement from the equilibrium bond length or the equilibrium length x. So this is the Hooke's law, we call it. The simple harmonic oscillator model obeys the Hooke's law. An elastic bond is analog to the spring, which possess a certain vibration frequency. At the minimum of the potential energy curve, the internuclear distance equals the equilibrium distance, which represents the bond length. The potential energy is described by the equation E equals to 1 over 2 multiply the K multiply the displacement square. So what you will see is that if we have a molecule of HCl, whereby the chlorine is much more heavier than the proton, and at this energy level, the proton will be vibrating, meaning that it will be compressed from the equilibrium bond length to this point here, or the hydrogen atom will be elongated to a distance at this position, okay, when it is elongated. So the positions of the hydrogen atoms will be changing throughout the process of vibrations along these positions and these positions at this energy. If the molecule gain more energy, then it will be activated to a higher energy level. Then at this higher energy level, the hydrogen atom will be vibrating along the positions of this point and this point through the equilibrium point. Okay, so you will see that the vibrational frequency will remain the same, but the amplitude or the bond length between the hydrogen and chlorine atom will be changing as they are vibrating at higher energy level. So similarly, in this image here, you will see that position 3 is the positions whereby the molecule is at equilibrium, where the bond between the two atoms are at equilibrium at this point here. As the molecule is vibrating along this energy level, then the bond length will be changing, okay, between this length and also when it is elongated at this length. If the molecule gain more energy, then the energy level will be increased from this level to this level. So the molecule will transit from one level to another level. Then at this level, you will be able to observe that from this image, the bond length for the molecule will be elongated to this extent, and at the same time, it will be also compressed to a shorter distance between the two atoms. For example, 2-hexanon. If we are focusing on the bond between the C and also the O at ground state, the state where the molecule has the lowest energy, when radiations of the frequency stated here is from the light source is shined towards the sample. So this frequency will activate the molecule for particularly the CO bond here, and it will be raised to a higher energy level. We call it as the excited state. Upon absorption of this energy from the light source, it will cause the bond of CO to be extend in the bond length during the vibrations, and at the same time, the compression will be further. So you will see that the bond of the CO become much more shorter when it is at the excited state compared to when it is at the ground state. And similarly, the bond of the CO will be further stretched at the excited state to a longer bond length compared to when it is at the ground state. Okay, so in order to activate the molecule vibrationally, then the molecule needs to absorb this frequency. And this frequency is particularly applied for the activations of the bond between C and O. Therefore, you will observe that in the IR spectrum, we can recognize or interpret the positions of the peak in the IR spectrum, which is corresponding to the vibrational or the CO bond at that particular frequency. The only changes after excitation is that the amplitude, the length of the molecule change, but the vibrational frequency remain the same when they are at the ground state and also at the excited state. For that, we also have seen the relation between the force constant and the vibrational frequency. Okay, so the vibrational frequency in the units of hertz is equals to 1/2 pi square root k over m, or for a molecule, the m is the reduced mass. So the K is the force constant, and the value of the K also tells the strength of the bond. Instead of we report the value in the unit of Hertz, usually we will apply the wave number as the unit in reporting the value of the vibrational frequency. So we have to convert the unit of Hertz to wave number by divide the vibrational frequency in the units of Hertz with speed of light. Therefore, the vibrational wave number for a molecule with two atoms is equals to 1 over 2 pi c square root k over mu. The mu is the reduced mass and the k is the force constant. From these equations, we can see the relations between the force constant, the strength of the bond with the vibrational frequency, and also the reduced mass of the molecule with the vibrational frequency. The vibrational wave number depends on the force constant and the reduced mass. The force constant is proportional to the stiffness of the covalent bond that connects the two atoms M1 and M2. So the higher the value of the force constant, the stiffer is the bond and the higher will be the vibrational frequency. For example, the infrared stretching frequency of this group will change for C single bond N, C double bond N, and also the C triple bond N. The stiffer the bond with 3 triple bond, the vibrational wave number is much more higher compared to the double bond and also the single bond. Wow, the effect of reduced mass on the vibrational frequency can be observed, especially if one of the bonded atom, either M1 or M2 in the molecule, is a hydrogen atom. Then it will cause the reduced mass to be roughly the value of 1. Okay, so for that, those of the molecule such as CH, NH, and OH bond, they will have a much higher vibrational stretching frequency than do those corresponding bond to a heavier atoms, such as the bond between CH and CO. The vibrational frequency for CH will be much more higher compared to CO. Next, what about if the molecule is substituted with the isotope? For different isotopically substituted molecule, the force constant will remain almost the same. So the K value for a molecule different in the isotope, that will be the same. The reduced mass for the system will change appreciably and cause significant change in the vibrational frequency. So, for isotopic substituted molecule, the value of K are the same for two different molecules by isotope. They have the different value of the reduced mass. For example, OH and OD. Deuterium is much more heavier than hydrogen atom. Okay, so the reduced mass for deuterium will be larger compared to the hydrogen OH molecule. Therefore, the vibrational frequency for OD, okay, oxygen bonded to deuterium, the vibrational frequency will be much more smaller compared to the vibrational frequency of OH. Okay, due to the reduced mass of the deuterium is much heavier than hydrogen atom. So what will happen if you substitute the deuterium with the tritium? What is the result then on the vibrational frequency when you compare between OH, OD, and O tritium? Tritium is much more heavier than deuterium. So if you substitute the deuterium with the tritium, then the reduced mass for oxygen bonded to tritium will be much more larger compared to oxygen bonded to deuterium. Therefore, the vibrational frequency for oxygen bonded to tritium will be much more smaller compared to oxygen bonded to deuterium or oxygen bonded to hydrogen. So now, calculate the wave number of a vibration for HCl molecule, whereby the force constant is 516 Newton per meter. Find out their vibrational stretching wave number, and given that all the parameters here, with the answer is 2987 wave number. So in order to solve the questions, we need to apply these equations to find out the vibrational stretching wave number equals to 1 over 2 pi c square root k over mu. You are given the value of force constant, okay? So your task is to find out what is the reduced mass. The reduced mass is equals to the mass, the atomic mass for hydrogen multiply the mass for the chlorine divided by the total of the mass for the molecule of HCl. So you have to find out this and substitute it into the equations, and then you will be able to look for the vibrational frequency. Here is the solutions. First, you look for the reduced mass. Convert the molar mass to the units of kg or g, gram, okay, by divided the molar mass with the Avogadro constant. After that, substitute the reduced mass into the equations to find out the frequency of the vibration. Vibrational absorptions require the interactions of radiation with the molecule. When a molecule vibrates, there must be a periodic alteration in the dipole moment. This will create a field that interacts with the electric field of the radiation. Absorption will occur if the frequency of radiation matches the natural vibration frequency of the molecule. This absorption will alter the amplitude of the molecular vibration. Example given here is the asymmetrical stretching of carbon dioxide. So during the process of vibrations, then it will cause the dipole moment to change. And the dipole moment change will create the periodic alterations. And these periodic alterations will interact with the electric field. Okay, so they will have the transfer of the energy to occur from the light source to the molecule. The equations given here is known as the transition dipole moment integral. So this integral, it will govern the transitions. For a homonuclear diatomic molecule, okay, the dipole moment will be 0, meaning that the mu nm is equals to 0, and all vibrational transitions are forbidden. They are not allowed to occur. Such molecules are called the infrared inactive because there is no change in dipole moment. Example of molecule which has no change in dipole moment during the vibrational motions are the homonuclear diatomic molecule, such as nitrogen molecule, oxygen molecule. Okay, so the homonuclear molecules, that do not have dipole moment change during the vibration. So that does not give an observable vibrational spectra. We call this molecule infrared inactive molecule. Whereas for heteronuclear diatomic molecules, the dipole moment is changing as the displacement passes through the equilibrium positions. And this molecule, we call it as the infrared active molecule. Now you know that in order for the molecule to be vibrationally active, the molecule must possess the change of dipole moment during the vibration. With that, only it can interact with the light source to generate the spectrum. So how much of energy is required from the light source in order to activate the molecule? And the energy of vibrations for a molecule can be obtained through the solutions of Schrödinger equation based on the simple harmonic oscillator results. And the value of this energy is quantized. The energy is defined by the vibrational quantum number mu. The value of the mu range from 0 to very high value integer. So the energy for the vibrational level is equals to V mu plus half multiply the Planck constant multiply the vibrational frequency. The unit is joules. Okay, so we can convert these units of joule into the wave number. And for the conversion, we have to divide the energy in joule with the Planck constant multiply the speed of light. Therefore, you will get the vibrational wave number for each level at different quantum number equals to mu plus half multiply the vibrational frequency in the units of wave number. If you substitute mu equals to 0, okay, into the equation, which means that at the ground state, mu equals to 0, the lowest energy for the molecule, the value of the energy is equals to 1 over 2 multiply the vibrational frequency. This energy is also known as zero-point energy. So at the ground state, the molecule still possesses some amount of energy which is related to the vibrational motion. So meaning that some vibration still exists in the molecule even though at the ground state. The Gauss selection rule for vibrational motion in a molecule dictates that the electric dipole moment of the molecule must change when the molecule is vibrating. In addition to that, the change of the vibrational quantum level is limited to either increase by 1 or decrease by 1. This is applied for simple harmonic oscillators model. So each of the vibrational energy level, okay, it has their respective value. When the molecule is at the ground state, the vibrational quantum number mu equals to 0. So the energy for the ground state is equals to 1 over 2 multiply the vibrational frequency. For the first excited state, the vibrational quantum number equals to 1. Then we substitute mu equals to 1 into these equations here to determine the energy for the first excited vibrational energy level, and we get the value equals to 3 over 2 multiply the vibrational frequency. We can do the same for the energy which at V mu equals to 2, mu equals to 3, and so on. Okay, so for the transitions to occur, the molecule will transit from one level to another level by change of the vibrational quantum number increased by 1. So what is the amount of energy required? Then we find out the difference between the energy for the excited state with the initial state. Okay, so for example, if the molecule it transits from V0 to V1, then the delta energy, the energy change is equals to vibrational frequency. Similarly, if the molecule is able to transit from V mu1 to mu2, then the energy difference between the level of G2 and G1 is equals to vibrational frequency. So for these simple harmonic oscillators, what you will see is that the energy difference between the initial state and the final state is remain as vibrational frequency, right? Because every of the transitions from G0 to G1, they required vibrational frequency amount of energy for this to occur. For G1 to G2, they also required vibrational frequency wave number of energy to conduct the transition, meaning that for each of these transitions, they will occur with the same amount of energy. And what will be observed in the spectrum? The spectrum will only show the appearance of one peak at the position of vibrational frequency. Okay, if you still remember how to generate the spectrum. So the x-axis is the wave number. Alright, so this will give you the absorption, for example. Then at this position, the value is vibrational frequency, omega OSC, oscillations frequency. It will not tell you the transitions arises from which level to which level, because all the transitions will occur with the same amount of energy according to this simple harmonic oscillators model. Before we move into how to solve the problem like the appearance of a single peak in the spectrum, let's look into some example, okay, on the change of the bond length upon absorptions of the energy from the light source. So as the energy is increased after the molecule absorbs the energy from the light source, the degree of the compression and also the extension, okay, will be greater. But the vibrational frequency will not change, okay. I have mentioned to you just now. So we can calculate what is the maximum displacement that can occur upon the absorptions of the energy from the light source. Within the simple harmonic oscillator model, if the energy is increased, the degree of compression and extension is greater, but the vibrational frequency will remain no changes. At maximum displacement, or we call it as the amplitude, the kinetic energy will transform entirely into the potential energy. Therefore, we have these equations here. Half multiply k amplitude square equals to half multiply the Planck constant multiply the vibrational frequency. Okay, so we can derive the amplitude, or we can calculate the amplitude using the formula derived from the energy relationship. Okay, so we rearrange these equations and obtain the value of amplitude. So amplitude is equals to square root the Planck constant divided by 4 pi square, the vibrational frequency multiply the reduced mass. And you can try to answer these questions. The oscillations frequency of hydrogen iodide and hydrogen fluoride molecules are 6.69 times 10 to the power of 13 Hz for Hi and 8.72 times 10 to the power of 13 Hz for Hf. So you were given the vibrational frequency for both of these molecules, and then you are asked to calculate what is the maximum amplitude of the vibration for Hi and also the Hf. After that, you have to determine which molecule has the weaker bond. And you can justify using the force constant. So meaning that you have to show that which one has the larger force constant and which one has the lower or smaller value of force constant. Because the force constant is related to the bond strength. To determine the amplitude of the hydrogen iodide, first of all, we need to determine the reduced mass. Again, reduced mass is involved in the calculations. Okay, I hope that you all understand and can remember how to calculate the reduced mass for a molecule. So the amplitude is related to the reduced mass. Okay, you have a Planck constant divided by 4 pi square and then multiply the frequency of the vibrations for Hi, multiply the reduced mass. You will get the value here and it can be converted into the unit of nanometer. Similarly, you can do the same thing for hydrogen fluoride molecule. So you will get the value of the maximum displacement, or we call it as the amplitude for the HF molecule during the vibrations at the ground state. So the force constant of Hi molecule can be evaluated. Okay, you have the reduced mass, you have the vibrational frequency, then you can find out what is the force constant for hydrogen iodide as well as for hydrogen fluoride. After that, you compare the value. So Hi molecule, hydrogen iodide, has weaker bond because the force constant is lower value or smaller value compared to the hydrogen fluoride. Okay, so now you use the value of the force constant to show that which molecule is much stronger bond compared to a weaker bond. According to the Hooke's law, which applied to the diatomic molecule, when the atoms move away from their equilibrium position, a restoring force is produced that increases proportionally to the displacement from equilibrium. And the potential energy for such a system increases quadratically with displacement. And this is shown in the parabolic potential energy curve that leads to the harmonic oscillations. But from the potential energy curve, we will observe that the restoring force increases indefinitely with increasing distance from the equilibrium position. However, this cannot be a correct description for a real molecule because when an atom are indefinite distance apart, the attractive force between them must be zero, and the potential energy then has a constant value corresponding to the total energy of the separated atoms. Therefore, an n-harmonic oscillator model recognizes that real molecules do not obey Hooke's law, and the restoring force is not proportional to the displacement. A more realistic potential function must reflect two properties. Number one is that the molecule dissociates when internuclear distance is much greater than the equilibrium distance, where R is very large than the R equilibrium. And second, the nuclei will repel each other when the atoms comes to very close to each other, which means that the R, the distance between the two atoms, is very much smaller than the R equilibrium. A more realistic potential function, the Morse potential energy curve, is used. At larger value of R, we know that the molecule dissociates whereby two neutral atoms are formed. And since they do not influence each other, the force constant is zero. And R can then be increased to infinity with no further change of potential energy at this part here. Therefore, the potential energy curve flattens out at this dE, where dE is the dissociation energy, okay, or dissociation constant from the bottom of the potential energy well. While at a very small value of R, the positive charges on the two nuclei cause mutual repulsion, which increasingly opposes their approaching each other. As a consequence, the potential energy curve is steeper than for the harmonic oscillators. So in this graph here, you see two types of the lines. One is the solid line, another one is the dashed line. Okay, so the solid line will represent the Morse potential energy curve, whereby the dashed line corresponding to the simple harmonic oscillators potential energy. Alright, so molecules are never at the lowest of this potential energy well. And the lowest energy it can have is at V equals to 0, or the vibrational quantum number equals to 0, which is the first line here. If we look into these two profiles for the Hooke's model and also for the Morse potential energy curve, the deviation found in the curve for a real molecule from that resulting from the harmonic oscillators approximations are due to the mechanical enharmonicity. And simple harmonic oscillators, it works very well at the low vibrational state at V0, V1, when the quantum number is small, because it describes quite nice as the true potential at the bottom. As long as the displacements are small, the harmonic oscillator will work. That's why we learn the simple harmonic oscillators at the beginning of this vibrational motions of the molecule. And then we have another parameter which is known as the D subscript 0. This is the dissociation constant from the lowest allowed energy level, which is at V equals to 0. To determine the vibrational energy, we set up the Schrödinger equation using the Morse function. The Morse function is necessary because a realistic potential function must reflect two important properties, where it includes the molecule dissociate when the internuclear distance is much greater than the equilibrium distance, and the nuclei will repel each other when the equilibrium distance or the distance is much less than the R equilibrium. So solving this equation reveals that the vibrational energy levels are quantized. The energy term G mu, which represent this quantized energy level in the units of wave number. Okay, so here the mu here represent the vibrational quantum number, which takes the value of 0, 1, 2, 3 up to maximum value. And the variable in these equations are omega E, known as the hypothetical equilibrium oscillation frequency. It is defined as the frequency the molecule would exhibit if it were vibrating exactly at the bottom of the potential energy well. Chi E is the enharmonicity constant. This term subtracts energy as the vibrational quantum number increases. and it caused the energy level to become progressively closer together as the quantum number increases. And here are the definitions for the hypothetical equilibrium oscillations frequency, the enharmonicity constant, which is also equals to the vibrational frequency divided by 4 multiply the equilibrium dissociation constant. And the dE is the equilibrium dissociation constant, which is the dissociation energy relative to the equilibrium. And this is the positions or the value for the D0 corresponding to the dissociation constant from the lowest allowed energy level, where V equals to 0 or the vibrational quantum number equals to 0 at the ground state, and dE, D subscript E, is the dissociation constant from the bottom of the potential energy well. Okay, so these are their respective definition. When we compare the energy, which is determined using the enharmonic oscillators model and also the harmonic oscillator model, we will see that this part here, V plus half, are the same for both of the model, and the harmonic oscillator's vibrational frequency is equivalent to the omega E multiply the 1 minus enharmonicity constant multiply V plus 1 over 2. So this is equivalent to the vibrational frequency. So we can determine the vibrational frequency equals to omega E multiply 1 minus chi E V plus half. And from here we can see that the molecular vibrations tends to oscillate harmonically for a small value of V, or at low value of vibrational quantum level. In low energy region, the second term here, okay, is small, and the energy level are almost equally spaced, which is similar to the simple harmonic oscillators. So we can further relate this, the enharmonicity with the force constant, as well as the vibrational frequency of the molecule. You may refer to this video to check out the simple harmonic oscillators and also the enharmonic oscillators, whereby both of them will show the very close similarities when the vibrational energy level is at low value. If we substitute the value of the quantum number into the equations for the harmonic oscillators and also the enharmonic oscillators, then we will get their respective value at different quantum level. Okay, so this stack of lines illustrates the value of the energy from the ground state to the first excited vibrational energy level, second excited vibrational energy level, and also third excited vibrational energy level with their corresponding value according to the simple harmonic oscillators model. But if you substitute the value of the quantum number into the enharmonic model, then these are the value, okay, for the respective energy levels. When we find out the energy difference between one to another level and compare the value of the energy difference between the harmonic oscillators and also the enharmonic oscillators, then you will see that for harmonic oscillators, the energy difference, okay, the gap between V0 and V1, V2 and V1, V3 and V2, the energy difference are the same. Okay, but For the enharmonic oscillators, the energies difference between one level to another level, they are not the same. Okay, if you try out to find out the difference between G2 and G1, as well as G3 and G2, you will see that the value are different from one to another. So what will happen is that the energy gap, the energy levels in the enharmonicity oscillators are not equally spaced. Therefore, the amount of the energy required for the transition to occur from one level to another level will be different, okay, in this enharmonicity model. So that will show the different positions of the peak in the spectrum compared to the harmonic oscillators, whereby you will only see one single peak to be appear in the spectrum, because the transitions, they all require the same amount of energy regardless of the level of the transitions. So if we compare the potential energy curve for the harmonic oscillators with the enharmonic oscillators, then we will realize a few features. Number one is that the molecule will dissociate in the enharmonic oscillators. Second is that the vibrational energy levels will get progressively closer as the vibrational quantum level increases. Number three is that the R equilibrium in the molecule is no longer the same for all the energy levels as deduced in the harmonic oscillators. So with these variations, it gives us to observe the presence of multiple peaks in the vibrational spectrum. You may visit this website to view the vibrational motions of molecules such as hydrogen chloride, carbon dioxide, and water molecule, their motions at different vibrational energy level. Then what is the effect of enharmonicity on the infrared spectroscopy? We can see that the selection rules is no longer restricted to the change of vibrational quantum level, either increased by 1 or decreased by 1. The selection rule for enharmonic oscillations is allow the changes which involve more than one quantum level. So we will have the delta mu equals to plus minus 2 or plus minus 3 or even higher, where higher vibrational transitions are allowed. For the enharmonic oscillators, the delta mu is arbitrary, but intensity are weaker for the transitions which involve higher delta mu than 1. The shift of the energy levels, where the energy levels will getting closer and closer as approach dissociations. And this is expect to see more transitions than a single peak in the spectrum due to the energy levels is getting closer and closer.